Hello everyone, in this video I'm going to do a review of exam 2. The second exam is structured essentially the same as the first, be in Canvas in a regular class time. The questions will be multiple choice, true, false, similar to exam 1 structurally, and also largely based on concepts. You will not have to download any worksheets or anything. You can have Excel open if you need to look up something or use it for a calculation, but you may not need it at all actually. You can also have a single 8.5 by 11 sheet for notes, front and back, written or printed is fine. And the exam covers the topics that we have talked about in this class since exam 1, so essentially since after the fall break. Also, this slide deck will be posted in Canvas along with the study guide that's already there in week 15. So during the first portion of this course, we focused a lot on descriptive statistics and on sort of performing the actions to calculate things from data or create a chart, learning about some functions that we can use, and a few of the tools that are in Excel. And then since then, since basically the second half of the semester, we started to shift to think about how we would approach solving problems with these tools, with Excel, with the tools that we have in it, our understanding and knowledge of the concepts behind data analysis and spreadsheet analysis, creating spreadsheet models and things like that. And so the focus of this last exam is also shifted in that way too, meaning the concepts are based on things that might actually be approached differently depending on the person who's trying to solve a problem. So a problem might be presented, and one student might choose one tool in Excel to solve that problem, and another might choose a different tool and get a positive, correct result. So that makes it a bit challenging when you're trying to learn how to shift and take advantage of the fact that you now know, kind of the fundamentals of Excel and, descriptive statistics, etc. So this sort of second half of the semester begins focused on making sure that we have a solid understanding of variables, of types of data. And we've done that before. Prior to the first exam, we talked about these types of variables and we've seen examples of them. But now it's even more important to recognize those variable types and what you do with them. So if you're presented with a set of data, you having the ability to look at that data and say, oh, I see categorical variables, labels, right? What can I do with those? Are the categorical variables part of the questions or the problems that are being presented that, someone, a teacher or an employer in a job are asking me to solve? So this table sort of summarizes the primary types of variables and data that we've been working with, to try to put them all together in one place so that you can review this and confirm for yourself that yes, I know what categorical is, I know what numerical means, nominal, ordinal, continuous, discrete. So those terms, what do they mean, and how do you detect when you have one of these types of data in a data set? So a categorical variable is largely just a label, usually a word or short phrase that indicates some sort of categorization. So on the far right, if we take a look at the examples, things like gender, color, marital status, blood type, etc. So if you remember from, I don't know, week 4, I think, frequency tables, where we had a column of categories, labels, and we had a column called frequency, and we had a column called relative frequency. And the first column being the labels, those are the categories, and then frequency is a statistical term that we use in this context to mean basically just how many of each are there. So if I look again at those examples and I say, well, let's say blood type. I have a list of the blood types, one per row. In the frequency column, the next column over, I might have, I went out and did a survey of people, let's say on the campus, and I asked 100 people their blood type, and I counted each one. So next to each blood type, there's some number. That's the count or the frequency, an integer in terms of data type. And then next to that, I had that relative frequency column, which is a calculation that I would make later to say what proportion of this population, 100 people, have blood type A. And that calculation is the total number, 100, divided into the count for blood type A. And then I end up with a relative frequency, some decimal number in the relative frequency column. So for one row, I see the category, the frequency count, and the relative frequency. So we would ask ourselves, okay, what kind of data are these things? Well, the label, blood type A, that's my categorical, right? And then the second value, the frequency or the count, is numerical. And if you take a look at this chart, it's discrete. It's a number, it's a count. It's an integer that is a discrete value, meaning it doesn't have a decimal portion to it. So this is an example. The example of counting up people's blood types is an example of here's a project, here's a problem that we need to collect data for. Once we have that data, then the next question is going to be, what do we do with that, right? What is the next step? So that's the data, the input that we're interested in. We're going to do some sort of processing, and then we're going to create some sort of output. And in Jagia chapter 4, under data visualization, that's producing charts. Now we've already produced charts prior to exam 1, and so what's the difference? Why are we talking about an entire chapter on data visualization when we've already looked at that? Prior to the break, when we were talking about charts, it was how to create one. Well, now we assume, okay, you know how to create one. Go into Excel, highlight your data, click the right insert, and choose a chart, etc., right? That's not the question anymore. The question is, how do you choose which chart to apply to any given data set? So using the blood type example, I have this frequency table. I have blood types, I have a count for each one, and I have relative frequency. The question would be, what kind of chart or charts would I use with that data? The reality is you could really use any chart. Okay, Excel will allow you to do that. I could highlight that data and pick literally any chart that exists in Excel. However, there are some data visualizations that are going to give you a better visual representation of that particular data set, that one is recognizable maybe by your audience, and two, that just lends itself more to that type of data. In that example, categories with some frequencies, for example. So what would that be? Well, one of the things that we talked about early in this course was the fact that bar charts are really good with categorical data. A bar chart would have the category names across the bottom, blood type A, B, whatever, and then each bar represents the count, the frequency of each of those categories. So in data analysis, bar charts are very, very commonly used in that kind of scenario. And so instead of saying, oh, that's about blood types, we want to generalize it even more and say, oh, that's the sort of formulation of categorical variables counted up in terms of frequencies and then also relative frequencies. So a bar chart works really well with the frequency. The next question would be, well, would I use bar chart for the relative frequency? Again, you could. However, the relative frequency represents proportions, percentages. 20% of this population has blood type A. Okay, what visualization depicts proportions, percentages really well? Could I use bar charts? Sure. Any of the others? Sure. But the one that represents it really well is a pie chart. A pie chart shows proportions really well. And so if the question or if the request was, we want you to look at this data and provide a chart for the relative frequency, the most common one to choose would be pie charts. Keeping in mind, really I could use any of them. Okay? But people are more accustomed to seeing that in that form because of the type of data, going back to that original sort of table that outlined the different data types, which is expanded here to show those types along with the most common sort of visualizations used with that type of data. We can simplify this a little bit also by just listing types of charts along with types of variables or relationships that we're interested in. So in this slide, we're showing if I'm interested in visualizing a single variable, like the frequency example a moment ago. Bar charts and histograms tend to work really well with that. If I'm interested in visualizing relationships between two variables, there's several listed here, etc. And so this is one of the things to start to get to comfortable with and to recognize as you're working with these. The next part of this, the next sort of step is once I begin to create visualizations, I see the images that my data is beginning to produce. One of the key questions is the question of correlation. We talked about this earlier in the semester with the Correl function, etc. in Excel, but now we're interested to expand on our ability to recognize when there is correlation and when there's not. As a reminder, correlation is the statistical relationship or association between variables. That is, to what degree does one variable change or affect, influence another variable? And we talk about these in ways such as direction, meaning is there a positive correlation? They both increase at the same rate or similarly, right? Or is there a negative correlation? As one increases, the other decreases. Or is there no correlation at all? They don't seem to affect each other at all. We also think of correlation in terms of strength. How strong is the correlation? Now we can use terminology for that. We can say this has a strong positive correlation or a weak negative correlation. We can also do it mathematically to use the correlation coefficient. We talked about that also earlier in the semester, and that's that range of values from -1 to 1. But for our purposes, we're currently thinking more in terms of using the terminology as we're describing our findings with regards to data. We also talk about correlation in terms of linearity. Most of the trend lines, for example, that we have seen so far in this course this semester have been linear. When we've shown a trend line, we draw it straight. and the correlation tends to follow that. So we see this, positive or negative looking line. There's also nonlinear, which is a type of correlation that shows where the relationship changes over time or over the span of the data. Instead of being a straight line, it actually is curved. And then there's an adage that we always keep in mind, is that correlation does not imply causation. And what that means is we may see correlation between two variables, but that does not necessarily mean one causes the other, or vice versa. Okay, it's possible that it does, but it does not necessarily mean that, or does not imply that. So as we're looking at graphs, trying to learn the terminology, learn to determine or detect characteristics of the data through seeing their visualizations. We talked about the term of skewness before, when we talked early in the semester about normal distributions, for example. The very first graph here on this slide shows what you would possibly call the normal distribution. It looks symmetrical. And that's a term that we might use if we see a data set that has been visualized and it looks something like this, where the left and right side of the mean look close to or very much equal. As opposed to that, we have skewness, ways in which data is either positively skewed, as shown here, or negatively skewed, as shown here. So as we're exploring these ideas, we think about ways in which we can use terminology and pictures together. And so if you see this column that has A through E, you might think about this in terms of natural language. How would I describe a visualization? So for example, the relationship between the two variables appears to increase at first, but then flattens. That's a natural language description of which of these 5 graphs. Well, if I look at them, I see that at the bottom, the relationship of these data points in this scatter plot seem to start out in a positive trend and then flatten out. This is also referred to as a nonlinear example, whereas the other 3 of the others are linear. If we take a look at the second one, the relationship moves in an upward direction. Okay, think about those terms. Upward, we generally think of upward as starting on the left-hand side at some low value and increasing as it goes from left to right. The next one is relationship between two variables, decreases at first, but then increases. This is also a nonlinear example where the relationship of the data is not in a straight line. The relationship shows a downward trend as one variable increases, the other decreases. And then lastly, the relationship of the two variables show no pattern or trend. So those are ways in which we might describe them. If someone said, hey, write a kind of a narrative, sentence or something about this data. The terminology that we've been using is more brief and is the more common way in which statisticians might refer to it as letter E, the relationship between two variables shows no pattern or trend. We would refer to that as no correlation. The positive linear correlation, the nonlinear example, the negative linear correlation, and also the last one being nonlinear. So through JAGA Chapter 4, we've been focused on data visualization, trying to take another step forward past just knowing how to produce a chart in Excel, for example, and what the fundamental statistics are behind that, and now trying to be able to recognize certain aspects and characteristics of charts or of data and what charts best depict that data depending on the types of data and the relationships between them. After Chapter 4, we moved on to spreadsheet modeling. Spreadsheet modeling refers to using software like Microsoft Excel to create models. meaning a mathematical or a logical way in which we might simulate real-world systems or processes. For a second, we can take the word spreadsheet off of this and say modeling by itself, because it's a concept used in many fields like engineering and computer science and economics, etc. In our context, we're interested in spreadsheet modeling given the types of data and concepts that we're working with currently. There's also a term, spreadsheet engineering, and that term is really the process of actually designing a model. And in this context, because we're talking about spreadsheets, that's the focus. But modeling in itself is also an engineering practice. Everything that we've been doing so far is spreadsheet modeling. That is actually implementing models, starting with data in a Microsoft Excel spreadsheet. We also should be aware that there's a couple of different types of models that we have been sort of exposed to so far. The first one is called deterministic, and that's when we know what the parameters are. One of the examples used previously in recent weeks was, for example, a personal budget. Let's say I have recorded all of my expenses. I have written down what my income is, what the taxes are taken out, and I'm interested to model ways in which I might increase the amount of money that I'm able to put in my savings account. All of those variables, all of the income, my expenses, etc., I know all of those. So that's called deterministic. Stochastic models are models that have some form of randomness in them, something that you don't have a value for, or you can't predict up front, or they have some sort of uncertainty. One example of that is the weather. I can model the weather, I can try to predict what the weather will be like tomorrow, but there are some random variables involved that I don't have access to and I may not know ahead of time. Because of that, we would refer to a weather prediction model as stochastic. So in any decision model, there are three critical components that it's important for you to be aware of. All models are going to need input, data of some kind. We generally do something to that data. We process it with calculations or whatever, and then we produce an output. Another approach to modeling is through what's referred to as influence diagrams. An influence diagram is a visualization that helps us illustrate different components of a decision or a scenario in the real world in which we're trying to understand. So often we're given a problem, and one of the ways in which we might try to understand that problem is to create a diagram like this, where the nodes or the circles are our variables and the lines are the relationships or the influences between those variables. So in this example, we have profit as our primary focus in terms of the problem domain that we're interested in. And we have mapped out the idea of revenue and cost. These are the two primary things that we would use to determine what our profit is. Revenue minus cost. Underneath cost, for example, we would break that out further and say, what is it that influences cost? Well, we have variable costs and we have fixed costs. We might ask, what is it that are our fixed costs? Well, labor is a fixed cost, operations is a fixed cost, etc. And then we can start asking questions with regards to our diagram. What is the primary target? In this case, it's profit. What type of variables do you think are these yellow nodes? We refer to those as intermediate. They're the things that we may be able to influence or change or modify in ways to possibly change or affect our problem domain. So if we're interested in increasing profit, are there ways that I can change my variable costs? Or is there a way that I can increase my revenue, etc.? The green nodes represent input variables. These are values that we get from some other source, some external source usually. And so we take that input and apply that to whatever calculations we have in our model to demonstrate, variable costs, fixed costs, our price, etc. And another way that we might actually say these things or express the way in which we think about these different nodes is like this question: what variables influence demand? What variables influence the variable cost, etc.? And so in this example with the demand, it's the roast and bean region. And we can also talk about what is it that does not influence one of the nodes, so on the far right side, labor and operations costs don't really have an influence on, let's say, price. As kind of an extension of spreadsheet modeling, we then moved into what-if analysis. And if you recall, what-if analysis is a way in which we help support decision-making by exploring the effects of changes that we may be able to affect in a model. Often these are done in an attempt to try to predict some potential outcome. So again, going back to my example of the personal budget, if I'm interested to increase the amount of money that I can put into my savings account, I might look at my costs and say, which one of these costs could I change, and what would happen if I were to reduce my cell phone bill? What if I change this, or what if I change that? So what-if analysis is a concept in statistics. It's not just in Microsoft Excel, but within Excel, we did explore 4 different tools that help support what-if analysis. We had data tables and Solver, GoalSeek, and the Scenario Manager. These are 4 things that you worked with through the homework assignments. I would recommend that you review those assignments and the quizzes that went around those tools to help kind of remind yourself what each one of them does, and also try to pay attention to how are they similar and how are they different between the 4 tools. So one of the ways in which you can think about it is to use this set of use cases and try to think, which of these tools might I use to work with these questions. So in the first example, a company wants to analyze how different sales volumes and prices affect total revenue. If I have the sales numbers and the prices, there's ways in which I might be able to use these tools to help ask what-if types of questions. So one of the ways in which that might be is by the use of a data table. If you recall, a data table is a way in which we can use what-if analysis to alter a variable to see the outcome of, in this example, maybe sales volumes and total revenue or whatever. One of the things to keep in mind too is, as said previously, spreadsheet modeling is often based on a generalized question or problem, and when that problem is posed to different people, the solutions might actually be approached differently and still arrive at a positive outcome. And so even though I put data table here, you may say, wait, I might be able to use one of the other tools. That's what I meant when I said try to compare them and think about the ways in which they're similar and which way they're different. In the next example, we have an airline needs to determine the optimal number of flights between cities to maximize profit. Okay, maximize profit. So one of the tools that we may be interested to use is Solver. If you recall, Solver has similarities with the Scenario Manager tool that's in Excel, but one of the things that is built into it that is somewhat a couple steps beyond what Scenario Manager does is the functions minimum and maximum that are built into it that helps with optimization. So that's this optimal number of flights. Sounds like a really good candidate for using the tool called Solver. A student needs to find the minimum score required final exam to achieve a 90%. Well, you're talking about a single variable. What is it that is the variable here? The minimum score. So the what if analysis might be, well, what if I get a 70? Does that get me to my goal of a 90% in the course? Oh, that's actually too low. So let me try again. What if I have to, what if I get an 80? Will that get me to that point? Notice that we're only changing one variable. That's one of the issues, the sort of characteristics of GoalSeek. It's a single variable tool, which in this particular scenario use case works well. And then Scenario Manager is very similar to Solver. In fact, their dialogues in Excel look really similar. Business wants to evaluate different budget plans based on optimistic, pessimistic, and more likely forecasts, right? So those are categories. Oh, that would make sense to use something like Scenario Manager or Solver because they have a similar structure in the sense that I can create multiple scenarios and have the tool calculate them together. That would not work. GoalSeek would not work in this case because we're talking about trying to compare numerous budget plans. You could use GoalSeek, but you would have to do it over and over and over, right? Rather than just letting the tool calculate all of them together. So between spreadsheet modeling and what-if analysis, these concepts kind of intermingle with each other. It's important to think about how you would use these tools along with the concept of being given a problem and you being the one to choose which tools to try to solve that problem. We then moved over to ethics in week 10. This is not in the textbooks. This is a Canvas material, if you recall. Textbooks has a very small amount of information about ethics. And there's also not like specific formulas or functions or anything like that. This is more conceptual. And so one of the first questions we wonder is, when we study ethics, what is it that we consider ethics? What part of business, for example? And you see in this definition, it's a set of principles or values, right, that guide the behavior and decision making. And we often refer to this as based on what we consider right, wrong, fair, just, unjust, etc. And so ethics is not necessarily a set of rules. They're usually referred to as a set of guidelines. So a couple of questions just for you to think about. Is there a single source of ethical guidelines? And the answer to that is no. We took a look at a couple of examples in the week we talked about ethics, and we used the American Statistical Association set of guidelines as one example, and we also looked at the Harvard Data Ethics Guidelines, which is another example, and there's some overlap between them. They both talk about transparency, for example, but they're also different, right? And so you kind of wonder, well, what makes them different? What is it that we might be expected to behave one way in one place and differently in another place? And that goes back to the term values in that definition. Different organizations, different cultures even, have different values. So what they believe is ethical in one place may be different elsewhere. And the other aspect is, are ethical guidelines and laws the same thing? The short answer is no, they're not. You can't be arrested for unethical behavior. You can be arrested for breaking the law, right? There's a difference between those two. So guidelines means sort of an expected approach to behavior, but not something that you could be arrested for. You could potentially be fired for in a job situation, which is obviously a different thing. So as I said, you don't have to memorize any full set of guidelines, but we are interested in some of the key terms that we explored and read about and saw through the Theranos case study, etc. And those are listed here. And this isn't that you have to memorize them necessarily. It's that you understand what they mean in the context of ethics. What does it mean to have integrity within, let's say, if you were a statistician, right? To be able to say that you follow a guideline with regards to integrity means that you use the tools that you have in reasonable ways, and that you demonstrate the ability to follow the guidelines that relate to the ethical production of your job, right? And there's transparency. We talked about that previously. Transparency means that if there are problems that they're revealed and talked about and worked on. Privacy and confidentiality tend to go hand in hand with regards to data. There's a lot of data like healthcare data, financial data, etc., which are private and should be kept that way. The Theranos case study was a really good example of misleading conclusions. And if you're performing ethically, you would avoid doing something like that. So that was a really good example. Taking ownership with regards to the job. If you're a statistician, you own your integrity. You own the idea that, hey, I take ownership of making sure that I'm doing the job the best way that I can. Intentionality is a key factor. Again, that was something we talked about in the Theranos case study. The intent to not follow the ethical standards would be considered unethical behavior. But if you have good intention, but you can still make a mistake, we're human, that's fine. That's not necessarily unethical behavior. And then, of course, being responsible for outcomes. What are the outcomes? And reporting those properly, etc. After ethics, the last set of topics are surround the concept of probability. We think of probability a couple of different ways. One is conceptually. We say that probability is the chance or likelihood that something will happen. One of the simple examples that I used in class was rolling a dice. If I have a 6-sided dice and I roll the dice and I ask you what number, would you predict this is going to roll, and you say a 5, and I roll the dice. The chance that the dice is going to come up a 5 is called probability. We don't know that until that event occurs, right? The other way that we can think about probability is mathematically. Probability is a calculation that the result is going to fall between 0 and 1, meaning I'm going to come up with a decimal value, likely, that is going to indicate what we would refer to as the probability. The chances of that 5 rolling up is a percentage out of the total number, which total possibilities in the case of a 6-sided dice is 6, right? And so the chances of getting a 5 is one of the outcomes of the 6 divided by the total number of possibilities, or 6, so 1/6. Also notice that this says inclusive. It is possible that the probability could be 0 or the probability could be 1. It's not possible, though, given our current knowledge, that probability is outside of that. So if you're doing a calculation in probability, and as I'm describing here, and you get a negative number or something larger than 1, then there's likely something wrong with the calculations. We have a few more terms within probability to be aware of. I've used a couple of these terms already in this review, and we certainly talked about them in class, but any process that leads to one of these possible outcomes, for example, rolling the dice, is called an experiment. The whole entire set of possible outcomes of the experiment, rolling a 6-sided dice, the total number of possible outcomes is 6. That's referred to as a sample space. On a 12-sided dice, the sample space would be 12, for example. On a coin, it's 2. And then an event is when I actually perform the action. In the case of rolling a dice, when I roll the dice and it comes up one of the 6 numbers, that's referred to as an event. If I rolled the dice 100 times, that would be 100 events. And then, of course, the result of the experiment. I roll the dice, it comes up a 3. That's my outcome, is the 3. 3 types of probability that we're interested in, and in this, at this part of our studies. The first is classical. Classical assumes that the outcomes of any given experiment are equally likely, meaning if I roll that 6-sided dice, it's equally likely that I'll get a 1 or a 2 or a 3, 4, 5, 6. I could potentially get any one of those numbers, and the probability of that is equal. And so the calculations for trying to understand that mathematically is quite simple. The probability of that event, something that we know is equally likely, is all the possible outcomes as the denominator, and the number of favorable outcomes. In the example of rolling the 6-sided dice, and someone says, I predict you're going to roll a 5. When I roll it, the number of possible outcomes is only 1. It's because they said one of the 6 numbers. We commonly abbreviate these things by using the letter P to indicate probability. Inside of parentheses, we might put a letter or a phrase or a word to indicate what our event is. So I could put, you notice at the bottom here I have P sub E, meaning the E is inside the parentheses, but that could say P of dice roll, for example, inside the parentheses. That labels our sort of experiment. The second type of probability is called empirical. This is when we have evidence or data to support our probability calculations. So instead of in classical saying everything is equally likely, in this case we say the probability of an event is based on collected observations, or maybe counting data or something. So we have other possible number of observations, meaning in our calculation, instead of saying this is going to be 6 or 12 or whatever, because we know that those are fixed numbers, we have to know how many observations are we talking about. So we collected empirical data on 1,000 observations. Our denominator would be 1,000. And then the number of times each of the event occurs. So out of those 1,000 observations, something has occurred, 2,700 times, or 27 times, sorry, then we would be 27 over 1,000, right? And again, that would produce a number between 0 and 1. The third type of probability, there are no formulas for. This is called subjective. This is a likelihood or a chance of something happening based on some sort of information, possibly intuition, some sort of estimation, experience, background knowledge, wisdom, whatever you want to call it. And there's no way to really quantify those things. If someone said, the last sentence here, based on my sense of the market, I estimate our sales will increase 10% next quarter. Well, what is sense of the market? There's no number that I can put on that. This is just intuition. And so we call this subjective. It's still considered probability because we're using that terminology to say, hey, I'm making a prediction. I'm making that prediction on something that I can't quantify, but I'm still making a prediction. And it is actually possible that they'll be right, but it's also possible they'll be wrong. So we can use this to discuss probability. We can use it to discuss the possibility of some, likelihood of something happening. But in this particular case, this type of probability, we don't really have a formula to plug in numbers to. If we did have data, if we did have some sort of empirical information that supports that, we would likely shift this back over to empirical probability. But if it's purely based on, say, intuition, then we would refer to it as subjective. So that's the review for exam 2. There are additional pieces of information. If you look at in Canvas, there's a sort of bulleted list study guide in the final or in the exam 2 module. I would recommend that you look through that list, and if there's anything that you're still not familiar with, use either of the 2 textbooks, depending on which topic it is. Remember that we used both books this time around. Both books have examples of most all of these things, so it's really useful to review those examples, especially if there's anything that you feel weak on. If there's any terminology that's not covered in this video or this review, or you don't find elsewhere, get in touch with a TA or myself. There's also a video from Dr. O, which covers it a little bit differently, similar topics, but it just has a different approach. So all of these things can help, and communicate if you need anything outside of that. Okay, thank you.